So, hello everyone, today I will start module 5 protein aggregation. So, the first lecture will see the introduction of protein aggregation. So, in the last module we discussed the protein surface interaction. So, very first lecture we just saw the what is the basic structure of the protein, its primary, secondary, tertiary structure, then function of different classes of proteins, then what are non-covalent interactions present in a protein apart from the peptide or covalent bond. Then we discuss the stability of the protein. After that we discuss how do we study or monitor the adsorption of the protein. So, we discuss with in terms of either adsorb amount on the surface or it change in its secondary structure. So, adsorb amount we discuss by labeling method, radioactive labeling, fluorescent labeling or staining. Then we can also go for the colorimetric method like Lowry method, Bradford method, BCSA, and a few instrument based method also we discuss like quartz crystal microvalence, SPR, ellipsometry. Also we discuss we can also monitor the viscoelastic property of the layer if you can monitor or analyze the dissipation energy of the adsorbed layer, and then change in the secondary structure. After adsorption we can analyze using circular dichroism or Fourier transform, infrared spectroscopy, FTIR. After that we discuss the how the protein adsorption take place. First step is the attachment followed by the reorientation. Then we discuss the simple kinetic model, how we can simply model the adsorption process to determine the different steps and as well as the rate constant or rate of adsorption. Followed by that we also discuss if there is a competitive adsorption, then how this adsorption process takes place. Then we discuss depending on the surface protein affinity, the larger proteins try to displace the smaller protein which are adsorbed in the end-on orientation. So, now in today's lecture we will discuss about the aggregation of the protein. So, as we know the function of protein depends on its 3-dimensional native structure, and when there is a change in the conformation it may also lead to the aggregate. So, we will just discuss what is the aggregation of the protein, how we can study or monitor whether there is a aggregation or not. Also we will briefly see after aggregation what are the effects of aggregation. Then next we will see in this lecture what are different factors like external factor, pH, temperature, ionic strength, even shear and the surfaces which how they affect the aggregation of the protein. Then we will discuss what are different intermolecular forces which are responsible for the protein aggregation. So, as I told, aggregation of protein, aggregation means a protein molecule is there in the native conformation. From the native conformation it unfolds. Once from the native conformation it unfolds or misfold a protein, and after unfolding or misfolding it can polymerize, means now the unfolded molecule is working like a monomer unit, it will form the oligomer, oligomer also we call as a nuclei. Then after oligomer then it goes to the aggregate, we also call the fibrils. So, call the fibrils. So, you can say simply aggregation means the misfolded proteins adopt a conformation in such a way that it goes for the polymerization. The first step is the formation of oligomer. followed by the formation of fibrils or the aggregate. Now, here in this step there is a role of external factors. So, these external factors causes a protein which is there in its native structure or native conformation to get it unfolded. Now, as you know, in case of let us consider the globular protein, it has a, you can consider hydrophobic core and hydrophilic shell. So, typically what happens when there is a unfolding, this hydrophobic core get exposed, and once this hydrophobic core get exposed, then it can interact with the other protein molecules, and typically when there is a hydrophobic interaction, or you can say hydrophobic interaction due to unfolding, then it lead to the formation of nuclei, then formation of the aggregates. So, somehow whatever the hydrophobic cores are there, that need to be exposed, and that is exposed during the unfolding of the protein, and once this hydrophobic patch of one protein, hydrophobic patch of other protein, they come closer. So, they form some sort of stacking, and that stacking looks like the fibrils. Now, we will just see if there is unfolding. So, unfolding means there is some loss of secondary structure, typically the loss of alpha helicity, and during the aggregation, as hydrophobic patches are coming together, it means there is a formation of more and more beta sheets. So, this protein aggregation is a major concern in case of protein research and clinical medicine. As we know, this proteins play very important role. Many proteins are also being used as a therapeutic drugs. So, whenever there is a role of protein, and depending on any external factor, it may get unfold and finally it may aggregate. So, this is great concern for researchers, particularly in the protein research and clinical medicines, because it is essential for the preparation of the protein, its storage, its transportation and its application. So, let us consider these are the protein molecules in the bulk, and this is a contact surface, because whenever we are storing or applying, it need to come into contact of a surface. So, there are two steps. First is when the protein molecules, of course, there will be the adsorption of the protein, and after the adsorption it may aggregate. So, first step is the surface induced, you can say this is a surface induced, and second, even in the bulk there are many protein molecule, and because of the environmental changes or some external factor, the protein molecules themselves may interact with each other, or you can say they agglomerate, and finally it will lead to the aggregation of the protein. So, this is you can say the bulk aggregation. So, protein molecules aggregate even in the bulk, also in the presence of surface. So, as I told, typically when there is a unfolding, so unfolding lead to the loss of the helicity. So, especially the helical structure is transformed or converted particularly to the beta sheets. So, here you can see there is a native protein, this you can see the native protein, and this you can see the unfolded or the aggregated protein. So, in case of here you can just see there is a mainly helical structure, few beta sheets, but here you can see the formation of many parallel or anti-parallel beta sheets. So, because of this formation of the beta sheet, the aggregates are also insoluble in aqueous solutions. This is native because of some external factors. Protein will expose its hydrophobic patches and then it will lead to the formation of beta sheet rich structures, and those structures as they are rich in the beta sheet, they also become insoluble. So, particularly if it is insoluble, so they get deposited inside the body or inside the cells, and the deposition of these insoluble aggregates or insoluble fibrils are associated with various diseases, and we will discuss quickly. So, this is a very simple fibril model of the insulin. So, it says this is the native insulin, we are showing the two molecules of the insulin. Now, during the aggregation, this hydrophobic groups protein first unfolds, then the hydrophobic groups here, hydrophobic groups of one and hydrophobic groups of second protein molecules, they are interacting and forming some sort of zipper structure, you can say dry steric zipper, and this is a characteristic feature of the fibrillation or aggregation of a protein. So, you can say this is typically the formation of the aggregates, or you can say formation of the beta sheet rich structure. Now, when there is aggregation of the protein, the first step is the native conformation of the protein is lost. It means the intended function of the proteins is also lost. So, the protein becomes functionally inactive. So, the first thing is the protein becomes functionally inactive because their native conformation is disturbed or perturbed. So, this is the first disadvantage or demerits of the protein aggregation. Now, second one, as I told, these aggregates are insoluble, so they get deposited, and these are associated with various conformational diseases, like I have listed few neurodegenerative disease like Alzheimer, Parkinson, prions. So, these are the few disadvantages, or you can say the adverse effects of the protein aggregation. The first is once its native conformation is lost, so its functional activity is also lost, or you can say now the protein is functionally inactive. Now, once it is unfolded, it will form beta sheet rich fibrils, which are typically insoluble and deposit inside the body or the tissue, and they are toxic and found to be associated with various neurodegenerative disease like Alzheimer, Parkinson's and prions. Now, we will quickly see if there is aggregation of the protein, then how we can understand it or how we can analyze it. So, the first thing we have to do various physical, chemical and biochemical assays. The first thing we go for the thioflavin T fluorescence assay. So, this is a particular dye which binds particularly to the stacked beta sheet structure, and if there is a aggregate, then only this particular dye binds and give the emission at a particular wavelength. And if you can monitor the fluorescence intensity, then we can confirm there is a presence of aggregates. Also, we can monitor the residual protein, as we discussed how to analyze the protein concentration or amount of protein. Let us say you can go for the colorimetric method. you can go for the Bradford, you can go for the BCASA, you can go for the Lowry method. So, typically during the protein adsorption, the change in the bulk concentration is not significant, but if there is a aggregation of protein, it means all the protein molecules are getting converted to the aggregates. So, in this case there is a significant depletion in the bulk concentration. So, you can monitor, let us say this is a bulk concentration, and that bulk concentration is also called the residual protein. This is with time, it will be depleted like this, and when it is depleted or completely there is no more bulk protein, then automatically the aggregation process will be lost, it will be stopped. Also, if there is unfolding or aggregation, there will be change in the size of the protein molecules. So, we can monitor or determine the hydrodynamic diameter. So, hydrodynamic diameter we can analyze using this dynamic like scattering or transmission electron microscope, and further as there is a unfolding and aggregation, it means there is a significant change in the secondary structure. So, we can monitor the change in the secondary structure, similar as we discussed for the protein analysis. We can use the FTIR or you can use the FTIR or you can use the circular dichorism. Then also, as we know, ultimately there is a formation of fibrils. So, these fibrils will have some length in the few hundreds of nanometer, in the range of 100 to maybe it may be up to the 1000 nanometer. So, this we can also analyze using the atomic force microscopy. If you can drop cast the aggregated sample on a surface and we can image with atomic force microscopy, we should be able to see the structure of the fibrils. So, we will quickly see how the TST works. So, this is a dye of the thioflavin T, its length is about 1.5 nanometer. So, what happens when there is a stack of the beta sheet formation, then this dye attaches to the beta sheet with its long axis. Long axis means 1.5 nanometer parallel to that of the fibrils. So, into the parallel of the fibrils, it binds towards its long axis, and once it binds here, then it gives a particular emission at 482 nanometer. So, if there is a absence of this particular conformation, in that case, although if you add the TST dye also, it will not give the enhanced fluorescence intensity. So, it gives the enhanced fluorescence intensity only if binds to the aggregates in a particular fashion, and that its long axis which is close to 1.5 nanometer binds to the plated beta sheet structure. And then we, once it is bind, we go for its fluorescence intensity measurement with excitation at 450 nanometer and emission at 482 nanometer. So, when we go for this fluorescence measurement, let us say this is time and this is the TST intensity. So, initially there will be the native protein. So, intensity will be low, then there will be formation of aggregates, it will suddenly increase, and once all the proteins molecules are converted, then it will reach to the plateau. So, this is typically it follows a sigmoidal curve, during the aggregation of a protein. So, this particular phase indicates it is a native protein. Here you can say this is like a oligomer, or you can say the nuclei, and this process is the fibrillation, and ultimately all the proteins molecule have been converted to the aggregates, or you can say there is no more, it has reached to the plateau, means there is no more bulk protein is available to form more aggregates. So, apart from the TST dye, we can also use the Congo red or the ANS dyes. So, other dyes can also be used, and as I told, if there is a unfolding, then definitely there is a change in its size or hydrodynamic diameter. So, that we typically use the dynamic light scattering. So, here we pass a laser beam through the samples, and the fluctuation of scattered lights are detected, and the fluctuation in the intensity is autocorrelated to get what is the diffusivity, or you can say the diffusion coefficient, and the diffusion coefficient is related to the hydrodynamic diameter using the Stokes-Einstein equation. So, it says the hydrodynamic diameter is inversely proportional to the diffusion coefficient. So, here Kb is the Boltzmann constant, is temperature, and eta is the viscosity. So, in this way, if there is a formation of different size of aggregates, so the value of diffusivity will be different, and accordingly we can monitor the hydrodynamic diameter. So, here I am just discussing this y axis, it is a hydrodynamic diameter of a protein. So, this experiment was performed at 3 different temperatures, 55, 60 and 65, and this is the thiophosphates fluorescence intensity on this y axis. So, what we are seeing is this particular protein, it was albumin. So, this is TST at 55, there is no increase, it means no aggregation. So, as there is no aggregation, so at this particular temperature, if you just see, there is no significant change in the DH value. So, this is the DH value is almost constant. So, we can say that TST intensity is correlated with the hydrodynamic diameter. Then, if you go for the 60, then this is 60, you can say there is an increase in the TST fluorescence, it means there is a formation of the aggregates, and accordingly we can see there is an increase in the hydrodynamic diameter or hydrodynamic size as well. Further, if you further increase the temperature to the 65, aggregation is further enhanced, TST intensity is enhanced, and parallelly the size of aggregates is enhanced. So, it says that the TST intensity, it confirms the formation of aggregates, at the same time it also indicates what is the typical size range of the form the aggregates. So, here if you just see this nature of curve, so we do not see a typical sigmoidal curve, because here the initial phase is almost absent. So, it says the formation of the oligomers is very quick. So, this first process, as we discussed in the last slide, the first process is very fast or it is absent. So, directly we are seeing the elongation and the plateau phase. So, here we can summarize, whenever there is a external factor. So, that external factor may be your pH, it may be the temperature, it may be the other ions, even it may be the surface, even it may be the shear. So, it may lead to the conformational changes, and in conformational changes, if the hydrophobic residues are exposed, they will lead to the formation of the oligomer, or you can say the multi-layer formation, that is sort of nuclei, and once the nuclei is formed, then again the monomer molecule will bind to the nuclei, they will form the aggregates or fibrils, and then fibrils will be released in the bulk. So, if you go like this aggregation process, so this we call the lag time. So, in this phase conformational changes as well as the formation of nuclei take place. Then there is a increase in the, or you can say the formation of the aggregation starts during the elongation phase. And once it is done, then it reaches to the stationary or the plateau phase. So, whenever these conformational changes or the formation of nuclei is very fast, so accordingly the lag time can vary. Lag time may be absent, it may be the extended, depending on the what are the conditions or external factors, as well as which particular protein is available. So, what are different factors? As I told, the pH. So, pH particularly it plays important role, because as you know the proteins molecules are having hydrophobic residues, hydrophilic residues, positive charge as well as the negative charge residues. So, protein, let us say protein A, it will have the 0 charge, at pi. Pi we call the isoelectric point, at its isoelectric point. So, when we change the pH below or above, it means there will be some net charge on the protein. So, typically if pH value is less than pi, then protein will have the positive charge, and if it is more than pi, a protein will occupy negative charge. So, once depending on the pH, protein may have different charge on its surface, and that may lead to the protein protein interactions, or you can say formation of the oligomers and the aggregates. Next factor is the temperature. So, if you increase the temperature, increase in temperature lead to the breakage of particularly hydrogen bonds and other intermolecular bonds. So, depending on the temperature, a protein will have a melting point. So, if temperature is greater than the Tm melting point, then at that temperature protein molecules is unfolded, and once it is unfolded, it may again go for the protein protein interactions, formation of nuclei and the aggregates. Similarly, there is a role of ionic strength. Ionic strength, it can affect the charge of the protein, even it can affect the solubility of the protein. Apart from the ions, you can also add some other salts. Those salts can also change the solubility of the particular proteins. So, for these two cases, whenever you are adding some extra ions or extra salt or some extra chemicals, they are going to interact with the proteins, which will cause the either change in its chemical potential, change in the solubility, change in its surface charge, and that again leads to the unfolding of the protein. You can say we are dealing with the solution. So, up to these factors we are dealing in the solution. Now, when it comes in contact with surface, so this we can say we are talking in terms of solution. In the surface there can be the shear, that shear can come from the its transportation, it can come from the contact between two surfaces, even it can comes when we are manufacturing the therapeutic protein during the agitation or even during the flow process. So, there can be external shear, and when it comes during the applications or storage, it has to be in contact with some surface, then there will be the adsorption. So, these two are the external factors which affects the aggregation of the protein. And of course, one more factor is the bulk concentration. So, if you increase the concentration of the protein, there will be the molecular crowding, that may also induce the protein-protein interactions. But particularly in the physiological condition, we can this effect of bulk concentration is not significant, because we cannot play with the concentration of a protein in the bulk, especially in the body condition or the physiological conditions. But in vitro experiment, if you vary the concentration of a protein, so with increase in the concentration also it will have molecular crowding, and that molecular crowding can also induce the protein-protein interactions, which may lead to the aggregation of a protein. So, here I have listed one recent study where the effect of temperature as well as the shear was studied. So, this is a albumin protein. So, if the temperature is above the melting temperature, we are going to have the unfolded conformation, and if the temperature is less than melting temperature, it is expected we are having the native like structure. So, if it is a native protein, we can monitor the morphology. Let us see, by this is the FM image, we can say very tiny particles, its size is about less than 10 nanometer. Now, in these two cases, so during the temperature we are applying the thermal energy. Now, the thermal energy, it may break the forces which stabilizes a native structure of the protein. Now, if you are going for the shearing, then we are applying the dissipation energy, and if the protein is unfolded, it goes to the formation of the fibrils or the aggregates, while if it is a native protein, up to the certain shear there will be no aggregation. Now, if there is a formation of aggregates also, so this aggregate is going to change the flow behavior of that particular fluid. So, if there is a no aggregation, it means the protein solution is following a Newtonian behavior, but if there is a formation of aggregates, it means there is going to be its increase in the viscosity, and that change in the viscosity due to aggregation, it follows a non-Newtonian behavior, and particularly in this case it was observed a shear thickening behavior. So, this is the effect of external shear as well as the temperature, and once the protein is aggregated, you can again compare the FM images. Here are few aggregates or few agglomerates, here are the elongated aggregate structure, and here are the large globular aggregates, and again you can say it is forming like a chain structure. So, we can analyze the morphology of aggregates by the AFM, atomic force microscopy. So, once there is aggregation, it is expected that TST fluorescence intensity will be enhanced. So, here again you are seeing this at 55, the melting temperature of that albumin is 63, the Tm is let us say close to 63 degrees centigrade. So, here the T is less than Tm. So, in this case we did not observe the enhanced TST fluorescence even thermal as well as during the shear. So, what it says, if the temperature is less than melting temperature, there is no unfolding. In that case, there is no aggregation of the protein. However, if you just see the case of 60, this is the case of 60, there is aggregation with time. Also, if you just see, if you apply the shear, again the aggregation is enhanced. It means once the unfolding is there, then application of shear is sufficient enough to form the aggregates. Further, if you just see the 65, this is the 65 only thermal, and again if you add the shear, again it is further enhanced from here to here. This was enhanced from here to here at 60. So, you can summarize that there is a irreversible unfolding of a protein if temperature is above its melting temperature. So, this is the role of thermal energy. Now, the dissipation energy which is generated during the shearing, it enhances or accelerates the aggregation process. Now, if you want to calculate the dissipation energy, we can calculate simply as a product of shear stress and the shear rate. So, if you simply multiply the shear stress and shear rate, we can calculate what is the dissipation energy. So, other factor is the surface. So, typically whenever a protein comes into contact of a surface due to various intermolecular interactions, particularly the van der Waals interaction, hydrophobic interaction, electrostatic interaction depending on the surface charge, there will be adsorption of the protein. Now, it depends how strong is the protein surface interaction. So, the protein surface interaction, it will decide both the amount of protein as well as its secondary structure. Secondary structure, you can say it is unfolding. So, depending on this interaction of surface protein, there may be the unfolding. If unfolding means there may be the polymerization of the protein molecules, it will form the nuclei, and after the formation of nuclei there will be the aggregate. So, here we are seeing the three surfaces, surface let us say surface 1 given by the circular symbol, surface 2 given by the cross symbol, this is the surface 3 given by the square symbol. Now, all these 3 surface, this is the TST fluorescence we are seeing, there is an increase in the TST fluorescence, means there is a aggregation, but at the same time what we are observing is, let's say this is a so this is the lag time for the in presence of surface 1, this is the lag time in presence of surface 2, and up to here there is a lag time in presence of surface 3. So, what it says is, depending on the surface properties, the nucleation rate, or you can say the lag time, varies, but once there is a unfolding or sufficient amount of the protein on the surface, it may lead to the aggregation, and once there is a aggregation starts, or you can say at the end of the lag phase, we cannot distinguish which is surface 1, 2, 3, because if you just see the rate of aggregation, almost all 3 looks parallel to each other. So, the effect of surface, particularly we can say it depends on the surface property as well as the property of the protein, and depending on the surface protein interactions, we can have the different lag time. So, this lag time, even it may be very long, in that case there will be no aggregation even in the presence of surface. So, what are the different intermolecular forces which is responsible for the aggregation of a protein? So, first, long distance force, the van der Waals interactions, if the protein molecules are there, they will try to attract, it is simply C to upon r to the power 6 plus C r to the power 12, attractive as well as the repulsive part. Also, we can have the short range forces like hydrophobic, hydrogen bonds, ion-ion interaction, and the dipolar interactions. Apart from that, there is a electrical double layer. So, these 2 forces, especially this dispersion van der Waals forces and this short range forces, we have already discussed. So, here we will briefly discuss what is the electrical double layer. So, what happened due disruption of the intramolecular interaction and the formation of intermolecular interaction, that may be between the protein salt or the protein surface, result in the loss of native conformation of a protein, which leads to the formation of aggregates. So, these forces are long range forces, van der Waals, short range forces, hydrophobic, hydrogen bonds, ion-ion and dipolar interaction. Also, there is a role of electrical double layer. So, what happened? This is, let us say, a surface is having the negative charge, it is kept in some solution. So, depending on the charge on the outer layer, there will be a counter ion will come and attach to the surface. So, there will be 2 layers, one layer counter ion will be bound, other will be the counter ion will be diffusing. So, when they bind, so that is called the external layer, and when they are diffusing, it is called the diffuse layer. So, in a stable solutions, or when the colloids are stabilized, it may when a protein is stabilized in a solution, the counter ion and co-ions are non uniformly distributed and they form a electrical double layer. So, some ions are surface bound, they call the Stern or Helmholtz layer, and some counter ions are diffused around from the bulk to the surface, and they are referred as the diffuse layer, and the whole formation of this stern layer and diffuse layer we call as a double layer, electric double layer. So, here if we just see, this is the charge. So, the first layer is the stern layer, this is very compact layer of the adsorb. So, in the stern layer it is already attached or bound on the surface, it varies in the few nanometer, and the other layer here is the diffuse double layer. So, the Coulomb interaction or the electrostatic interactions of the charge group pulls the counter ion back towards the surface, but at the same time some repulsive forces repel those counter ion away from the interface. So, this is the diffuse layer and this is the stern layer. So, from here you can say this thickness is the stern layer and this thickness you can say as a diffuse layer. So, during the stern layer again there is a decrease in the surface charge. Let us consider the thickness of the stern layer is the d. So, the potential or you can say the electric potential here vary with the x, that is proportional to the charge density in the bulk or whatever was there at the surface here divided by the dielectric constant. Now, if we just see here it is following a linear. So, linear means you can say y is equal to mx plus c. So, you can write potential x is equal to this is the m plus c. So, if you compare these two equations, you can say potential on the surface upon d is equal to the charge density divided by the dielectric constant. So, depending on the thickness of the stern layer, we should be able to calculate what is the charge density or what is the potential, electric potential during the stern layer. Now, if you go for the diffuse layer, in the diffuse layer it exponentially decreases, and in that case the change in the potential with x is exponentially related, like psi naught e to the power minus kappa into x. Now, 1 upon kappa is known as the Debye length. So, here you just see this is charge is the let us say psi naught, when it becomes to the psi naught upon e. So, this particular distance is known as the Debye length, or you can say the distance from the surface into solution up to which the effect of surface is realized by the ions. So, that is known as the decay length. In other terms, it can also set the thickness of the electrical double layer. So, Debye length is the thickness of the electrical double layer. So, whenever we have any bulk molecules and we are going to measure its zeta potential, a surface charge. So, it is most likely that we are measuring the value of potential at the distance d, and its value will be in the range of, or it will be the less than that of the actual the surface potential, or you can say is less than that. So, this Debye length we can calculate depending on the, if you know what is the salt. So, we typically calculate using this equation. The kappa is calculated like the number density, this is the number density of particular ions, number density per meter cube. This is Zi, what is the charge of that particular ion, electron density upon the dielectric constant, K is the Boltzmann constant and T is the temperature. So, if you are having NaCl, so it is 1 electrolyte. So, in this formula all other parameters are known, Z is known, E is known, epsilon naught, epsilon we can take for the water, 75, K is constant, Boltzmann constant is, you can assume at particular temperature 25 degree centigrade. So, at 298 K we can calculate for 1 electrolyte like NaCl, 2 or 1 electrolyte that calcium chloride, 2 like MgSO4. So, here if you are varying this different electrolyte means you are changing this value of the Zi, and what is the concentration. So, accordingly this number density will also change. So, we can calculate the Debye length. So, it says that the Debye length is inversely proportional to the concentration. So, the thickness of that layer or what is the effective range where that electrical double layer works, it depends on the concentration of the ions present in the solution. So, this is we discuss about the individual ions. Now, let us say blood plasma, it will have different ions. So, similarly for the different ions, let us say it is having the sodium, potassium, calcium, magnesium, also negatively charged chloride, carbonate, phosphate and sulphate ions. So, we can calculate, it is asked to calculate the Debye length at 36 degree centigrade, take the dielectric constant at 74.5. So, here we can simply number density depending on their concentration, Zi for sodium it is +1, sulphate it is -2, electrical E electron charge on the one electron, epsilon naught is constant, epsilon value is 74.5, K is the Boltzmann constant, T is the temperature. So, we can calculate what is the value of Debye length, and if you calculate its value will come out to be 0.78 nanometer. So, depending on the salt concentrations, we can also change the electrical double layer, and that depending on the concentration, the thickness of the double layer or Debye length we can increase or decrease. So, it will ultimately also determine the strength of protein-protein interactions. At the same time, it will also determine the stability. So, electrical double layer will have both the roles, stability as well as the protein-protein interactions. So, in today's lecture we started with what is the basic of the protein aggregation, then how it proceeds starting from the unfolding or misfolded protein, its polymerization to oligomer, then the fibrils or the polymers, then how we can characterize the aggregation process like TST, fluorescence intensity, its hydrodynamic size, even in case of residual protein, its morphology. Also we saw because of the unfolding of the native conformation, protein is functionally inactive, also it is associated with different neurodegenerative diseases. And then we saw what are different factors which affects the aggregation of a protein. External factors in the bulk like pH, temperature, ionic strength, in the presence of surface like shear and the adsorption process. Then we quickly saw what are different intermolecular forces like the long range forces, short range forces and the electric double layer. Thank you.